What is up, YouTube, and welcome to episode 65 of the Chaos Daily. Let's get into it. So, we left off yesterday talking about the idea of testing wings. Let's explore what our options are. The best way to go about this. And it's ironic that I'm doing this at the same time as that I just watched Mike Patey's video where he's discussing the wings that he's going to build for his scrappy bush plane. Timing, huh? What do you know? Anyways, so I'm facing similar problems to what Mike Patey's probably facing with his design for his wing. I have to deal with not so much the aerodynamics of generating lift and everything, but I'm dealing with the constraints of strength to weight ratio. How much structure can I get away with? How much strength can I get out of a given winged structure and make it as light as possible? What types of structure are going to be the best? These things are affected by how it prints, how it interacts with the spars, or how it interacts with the skin to structure distribution. How much ribs do I have? What angle are they? Where do they interact with the skin? How thick is the skin? There are a lot of these variables that go into designing the internal structure of a wing for resin printing, the same as FDM printing. The constraints for FDM printing are probably more numerous because there are a lot more printing constraints you have to deal with. There are also a lot more material constraints you have to deal with, and the way that the material is laid down by the print head. So long story short, there's a lot of questions I have and not enough answers at the moment. I have some ideas, I have some theories, but the only way I can test that is to actually print and test the parts. So what I've done is I've designed a series of wing structures. What I'll be doing is I'll be printing a wing structure that is about 200 mils long and about 100 mils in chord length. This will mean that I can get a good indication of how the structure is going to interact with a wing that is very similar to this. Absolute comparison between the thing I'm printing as a test article and the actual resulting design that I use in a wing like this. You could ask, why aren't I printing smaller versions so that they print faster, use less material, saves time and money? The short answer is that won't give me an accurate indication of the properties, the strength and structural properties of that part if it's made smaller. I have to make it pretty much the same to get the same kind of results that I would if I had then used that structure in this wing. If I make it smaller, then the force distribution across the skin or the internal structure will be vastly different depending on the ratio of size and scale. Those things don't scale linearly. There's a lot of volumetric properties that come with things. The same with, like, if you look at the strength ratio of a rod, if you double the diameter of the rod, you get something like triple the strength. It's not a double. So yeah, there's a lot of things like that are involved that I don't want to have to be dealing with. So I will print the wings as I would be using them. I'm going up to 200 mils long. There's another reason for this. Before, when I originally designed these parts, these sections, I designed them at 150 mil tall. That's because I intended to print them in the printer like such, so that I could get a nice clean skin surface. But what I discovered is that the interaction between when the ribs are pulling off the FEP sheet, it caused a lot more deformation to the skin. So it turned out better to turn them this way and print them on the tailing edge. And that way the ribs would be a consistent force of tension being pulled off the FEP sheet for every layer. You wouldn't get some layers where you'd only have tension for the skin, the cross-section of the skin, and then other layers where you would have a full cross-section with the ribs included, and there would be a lot more tension, and that would cause a lot of stress to the layers above. So printing things like this gives me a couple of advantages. It reduces the differences in tension for lifting throughout the whole print. So you get more of a normalized lifting tension throughout the whole print. It also allows me to print longer parts. I have a 250 mil long print bed. So I can go from this 150 mil up to 200 mil. I can even go up to 220, but I think 200 is probably a good fair size to get a good indication of the strength of the part, the properties of the structure inside, and all of that jazz. So yeah, that pretty much covers the reasoning behind it and why I'm doing it. Let's go over what I have planned. So on the USB stick at the moment, I have three wing sections. They follow a very similar profile to this. It is 200 mil long. It's 100 mils chord length at the root and 75 mils chord length at the tip. It is also a tangential loft, which means it comes out tangential to the root and then slopes, so I get a curve to it. This is going to give me a good variation of internal structure to skin interactions. It won't just all be straight lines or just the curve of the airfoil. There'll also be a curve on the leading edge as well as a straight and slight curve on the tailing edge. This gives me a very good broad view of the different interactions that we'll be looking for. So first up, I have the first three that are loaded on here are just shells. I'm going to ask the question, is the simplest solution the best solution? And that is, do I just take the airfoil of the wing and hollow it out? So what thickness of skin is required before the airfoil becomes self-sufficient in its own structural integrity? So we'll be going from a 0.5 all the way up to 2 mil thickness, 3 versions. So 0.5, 1 millimeter, and 2 millimeter. And we will see at what point it's strong enough to hold its own shape, and at what point it is a balloon, because at 0.5 millimeters, even resin acts like a balloon skin. Next up, after this print, because they are 12-hour long prints, they do take a little bit of time, we'll be looking at the conventional scale, full-scale type rib system that I've designed in here, where you have longitudinal ribs that are all evenly spaced across, and then there are holes cut out to make it lighter. Exactly the same as this, very similar, but we will be varying the distance between ribs. So we'll be varying the spacing of the ribs as well as the thickness of the ribs, I believe. Yes, one of them is 0.5 millimeters, the other one is 0.75. So this is 0.75. We know that this works. This is a very good combination of rib spacing, rib thickness, and all that, but it's too heavy. So we want to try and go lighter than this. So I'm trying a few others that are 0.5 mil thickness with varying rib distribution. So that's the other one we're trying out. The next one we're trying out is very similar to what you see in FDM printed planes. The crosshatch, where the ribs aren't just parallel, they intersect with each other. Same holes running through this inside to try and keep things comparable as possible. The same amount of hole profile is removed from both the parallel as well as the crosshatching. So we can see a good comparison between how much weight reduction we're getting between a parallel rib system and a crosshatch rib system. And then after that, I have a bit of a weird, quirky one. I've created 3 circles and an axis along the length of the wing, and I've created a spiral pattern of those 3 circles. So I've extruded those as a helix. I then mirrored it so you get a lattice of those 2 spirals crossing each other, and then repeated the pattern up and down so that we get these cross lattice helices running the chord of the wing. So we'll have a look and see how that works. I've got a couple of variations with that, as well as variations of that with the variation on the skin thickness, going between the 0.5 up to 1 millimeter. And then between those, there's a difference in the thickness of the lattice structure itself as well, going from 1.5 millimeters to 1 millimeter, I believe. Yes. So that covers those. The big one, the big kahuna, the one that I would love to use on everything, because A, it looks good, and mathematically it is the best way to go. It is the best structure to weight ratio you can get for a surface, and that is triply surface geometries, or gyroids. They are the holy grail. If I can get them to work, that'd be great. At the moment I can't. I'm having some issues with the gyroid pattern, introducing errors in the pattern. So when you go to use the Boolean operation to subtract the outside gyroid and only leave the gyroid on the inside of the volume of the wing, it won't do it. It just won't Boolean it. So the only thing left for me to do then is to export the gyroid or the wing as an OBJ and load it into something like Blender, and then try and do that sort of Boolean operation in there. There are other couple of softwares that can do the same thing. I have Blender. I'm kind of familiar with it. I come from a background of using Autodesk Maya, so I'll figure it out. There's plenty of tutorials on YouTube about gyroids and stuff for things like 3ds Max, Blender, all those sort of things. There's nothing on any CAD. There's no CAD tutorials. There's plenty of white papers of people talking about how they created these Voronoi patterns or gyroids, but very few actual practical implications of these things, like plugins or anything. There's nothing. I've looked. There's very little that I can just get my hands on and use. A lot of it's going to have to be, I just have to work it out for myself. And there's absolutely no tutorials online for how to create a gyroid in CAD. let alone in Inventor. A lot of them that I did find were cheating, where you first start with something like Blender or 3ds Max, and then you export it into Fusion 360 or something, and then it still doesn't work in Fusion 360. So yeah, there's a lot of that going on. But I'll keep working on that. But the problem is, if I have to export the wings and stuff into another software package to do the final operation to create the internal wing structure, that's an extra level of complexity that is going to sort of disqualify this structure type from this test series, because that's too much work for something that doesn't even account for things like ailerons, servo hatches, any kind of internal structure for the spars, stuff like that. All of those things just add levels of complexity in how they interact with the gyroids, and you have to use those Boolean operations then in another piece of software. It very quickly spirals out of control. So we're gonna try those out. I'm gonna get this print started, and we can see the results tomorrow. So we're gonna leave it there for today's episode. A lot to go over, I know. I'm sorry, but hey, this is really interesting stuff. One of my patrons, Jotham, he's like, dude, you could probably do a PhD in this shit. And I'm like, cool. What's a PhD gonna do for me? I'll take the research grants and the networks of people helping me on the topic, but I don't need the PhD. I'm doing YouTube videos. This is my calling. So yeah, as always, I've been Chaos. Make sure you hit the like button. Make sure you subscribe. Go subscribe to my other channel if you haven't already. And watch the video twice. That really does help out. And until next time, expect the unexpected. And I will see you guys later.
And a special thank you to all my patrons that help support the channel. If you would also like to support the channel, there's a link in the description.